Yeah. I will see. I'll look into it. Yep. There's no S? Okay. Why don't you go do a research project on LHospitals and tell me after that. I know it looks like hospital. It's LHospitals. Oh, we're gonna do a little hospital. That's horrible. LHospital. 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 We're gonna do some LHospital. Yeah. Okay. LHospital. Okay, so LHospital's rule, and so it's hard for you guys to see until you kind of go further down the realm into mathematics and other branches. But calculus opens up just an amazing number of opportunities to work with some otherwise very difficult problems. Now, this is not a difficult problem. We know how to do this problem right here, okay? But I'm going to show you how to connect this to a much more difficult problem and understand its, the nature of how it would handle. So we're going to look at the limit as x goes to infinity of 2x minus 1 over x plus 1. So first, we're just going to solve it algebraically. Do you remember how we solved this algebraically? Yeah, what do I factor out of the top? I factor out an x. I get 2 minus 1 over x. Divided by, what do I factor out of the bottom? An x. And I get 1 plus 1 over x. Now, as x goes to infinity, what happens? Right, these portions become 0. And the x's cancel, and you're left with 2 over 1, which is 2. So we know that this limit is 2. But I think that we would understand better well, no, but Kyle's right that if you looked at this derivative, the derivative of the top is 2. But if you were to take the derivative of this entire function, you would not get 2. So, yeah. Right. Right. Let's look at our calculators. Take out your calculator. Oh. So we have y1, y2, y3, y4. We're simply going to use y1 and y2. And what I'm going to do is I'm going to enter those functions. And I'm going to enter 2x minus 1 for one of the functions. And on the bottom, I'm going to enter x plus 1. Okay? And I'm going to change my window. I'm going to look at an x minimum value of -1 to positive 10. And I'm going to look at an y minimum value of -1 to positive 10. Actually, let's go to 20. Okay, everybody there? Now, watch the graph, okay? These are both lines. And what we are really doing is this function right here, y equals 2x minus 1, that's on top, right? And the x plus 1 is on the bottom, correct? We're allowing these functions to go to infinity, and we're finding what the quotient would be as they approach infinity, or the, one divided by the other. Now, look at this as they actually intersect right here, don't they? They intersect right here, right at that spot. So if I did 1 divided by the other at that spot, what would I get? I would get something divided by itself is 1. Okay? But look at over here. Look at the space here. How does this height compare to that height if you were to give it a guesstimate? Yeah, it looks like this one right here is a little bit taller than that one. Maybe it's 50% taller. Maybe it's 2/3 taller. Let's go into our tables and see exactly what that ratio is approaching. If we go to our tables here, and I go, say, 1, I'm going to go 10, I'm going to go 100, I'm going to go 1,000, 10,000. Very good. Do you see that the one is about twice as tall as the other? Does that make sense? Well, look, what's the rate of the one compared to the rate of the other? One has twice the slope of the other, does it not? In fact, in this situation, now you wouldn't have to do this because we've been able to solve it algebraically, but what you couldn't do instead is this. You could say the limit as x goes to infinity of the derivative of 2x minus 1 over the derivative of x plus 1. What's the derivative of 2x minus 1? What's the derivative of x plus 1? 1. And so that is our limit. So the rate of change ends up working out for the derivative overall. Now, it doesn't work that way every single time. There are special cases that we have to apply to this situation. Why is this interesting to us? Because if I asked you guys to find this limit, you couldn't do it. The limit is x goes to infinity of e to the x minus 1 over x squared plus 3. We have no idea how to do that right now, and you can't do it algebraically. Well, we can apply L'Hopital's rule and find a good way to solve problems like this. So do you see the problem that we have? Not all limits we could solve algebraically. Agreed? L'Hopital's rule involves rates of change of the functions that are being divided so that we can apply this rule. Let's now write down L'Hopital's rule. Yes, it looks like the hospital. No. So suppose that we're approaching a number and that the limit of that function is going to be 0. So if we put that in a quotient, we'd have 0 over 0, and 0 over 0 is very confusing. Or let's suppose you had this. The limit as x approaches a of f of x equals plus or minus infinity. Gotta be. Again, it's not plus and minus infinity. It's not both at the same time. It's one or the other. So we could just write it out, a third rule instead. That was the other one. In other words, we have 0 over 0 or infinity over infinity. Okay? At 0 over 0. Then, this is L'Hopital's rule. The limit as x approaches a of f of x divided by g of x is going to be equal to the limit as x approaches a of f prime of x divided by g prime of x. So we can shortcut our way around this by finding the rates of change of the function at the given point. But it must first satisfy those initial conditions. You have to have an indeterminate form. So you can't just do it with any type of function. It has to be indeterminate at a given point. I'll show you. You weren't done? 5, 4, 3, 2, 1. This is page 494 of your book that we pulled L'Hopital's rule from in case you want to reference. So let's go to the two examples. Ella brought up a very good one. Let's say the limit as x approaches 1 of x to the third minus 1 over x squared minus 1. Now, in that situation, we know how to solve that algebraically very easily, right? I'm just bringing it up to prove a point to Ella of exactly what's happening. Can we simply substitute the 1 in? No, we can't. You can't. Right, you would get 0. Now, we learned even earlier on that we could factor out an x minus 1 and cancel off the, what do you want to say, the discontinuity point. But L'Hopital's rule says we could do something much easier. If you were to substitute 1, you would get 0 over 0, which is indeterminate, correct? That's what it means. 0 over 0 or infinity over infinity we'll refer to as indeterminate. Unknown value. So what we're going to do instead is we're going to apply L'Hopital's rule. Limit as x approaches 1. I take the derivative. What is the derivative of x to the third minus 1? 3x squared. What is the derivative of x squared minus 1? Plug in your values. Over 2. Whoop. So now you can plug in your values. Yep. That would tell you your limit. Now look at this example, okay? Let's try one that's a little bit different, okay? Well, yeah, so if we let, if you look at the natural logarithmic function, okay, as we turn this on, as we go to y equals, if you were to punch in, say, natural log of x, and you go to graph, as x goes to infinity, y goes to Infinity. It goes rather slowly, doesn't it? But it does go to infinity. So if you were to plug infinity to this, e to the infinity would give you infinity. Natural log of infinity would give you infinity. And so you come up with an indeterminate form. So what we could do instead is we could take the derivative of each and look at the rate of change. So I have the limit as x approaches infinity of, very good, e to the x over 1 over x, which is going to be x e to the x. The derivative of natural log of x is 1 over x. I multiply by the reciprocal. Now, let's think about this, you guys. If you take a very large number times e to a very large number, what are you going to get? A very large number. So this limit ends up being infinity. So this limit does end up being infinity, okay? Yep. Okay, try one on your own. See if you can do that. First, always start by verifying that you do come up with an indeterminate form, okay? So, as we take the derivative here, if you were to plug in 1, if you were to plug in 1, you get 0 over 0. So we say it's of indeterminate form. So therefore, we need to apply L'Hopital's rule. And L'Hopital's rule says we could take the same limit, the limit is x approaches 1, and we take the derivative of the top and the derivative of the bottom. Question. Then you would apply a different method. No. Nope. So I showed you an example earlier that was not indeterminate, and so then you need to apply a different method. Okay, let me do this real quick. Okay, so I have the limit as x goes to 1. What is the derivative of natural log of x? 1 over x. What's the derivative of x minus 1? 1. So you get the limit as x approaches 1 of 1 over x. Can you now substitute the 1? Yes, and you get 1. Let's look at a different kind of example. We have the limit as x goes infinity of e to the 3, or e to the 3x divided by 4x squared. So if you were to plug in infinity, what would this part be? Infinity over infinity. So therefore we have an indeterminate form. So now what you need to do is you need to apply L'Hopital's rule. And it says, yep, very good. So we're going to apply the derivative here. What's the derivative of e to the 3x? 3e to the 3x. They use the chain rule. And what's the derivative of 4x squared? 8x. Now, let's look. If you plug in infinity, you still end up with I still end up with an indeterminate form. So now we're going to apply it again. So I take the, very good, 9e to the 3x. And, right, so you get an extremely large number over a small number. I mean, this is going to be infinity. I mean, this is like 9/8. I mean, it doesn't matter if you get infinity over 10, infinity over 20. It's still going to go to infinity. Oh, great question. So as soon as people see this, they want to use the quotient rule. That's not what L'Hopital's rule says. In fact, some people on their test last year, they got to this section of L'Hopital's rule, which I thought was going to be easy, and they did the quotient rule for every single problem. And we will not do the quotient rule at all with L'Hopital's rule. And so you have to make sure that you apply the appropriate strategy, okay? So you have to do that. Okay, there's some more difficult examples. Let's just pause there for today. I'll give you some easy problems to try today. I'll give you a little bit harder problems to try for tomorrow, okay? Okay, now you guys, there's a good place to start. We'll try more difficult problems tomorrow.